I want to tell you about the uncertainty principle that's rarely mentioned in typical quantum mechanics courses, but deserves to be much better known. The Schrödinger uncertainty principle. That's right. Erwin Schrödinger improved the famous Heisenberg uncertainty principle back in 1930, and no one told you about it. I'll show you how he did it and why it was a significant improvement. Okay, so what's wrong with the Heisenberg uncertainty principle, and why did Schrödinger modify it? Well, there's absolutely nothing wrong with it, but as is often the case in mathematics and physics, it can be very helpful to find a more general result. So instead of just having an inequality that relates uncertainties in position and momentum, it would be much better to know what would occur if we considered any two arbitrary observables. Now, by one of the axioms of quantum mechanics, every observable is described by a self-adjoint linear operator. So this would amount to looking for a relation that could hold for any two self-adjoint linear operators. And this is precisely what Schrödinger sought out to prove. But before he did, there was another slightly less general relation proved by the mathematical physicist Heisenberg-Robertson. In a paper published in 1929, Robertson showed that any two self-adjoint linear operators A and B must satisfy this inequality, where the right-hand side means to first evaluate the commutator of A and B, then take the expectation value or average of the result, and finally to take the absolute value and then square it. This result has come to be known as the Heisenberg-Robertson uncertainty principle. You may also have seen this in some textbooks referred to as the generalized uncertainty principle. And it is indeed a generalization of Heisenberg's principle. You can easily check it by just plugging in the position and momentum operators and evaluating. The result is exactly the same. So Heisenberg's uncertainty principle is just a special case of this more general principle. The real power of this general principle is that you can now plug in any two quantum observables and immediately see what sort of uncertainty relation exists between them. And there's a really nice way to visualize this. Let's take two observables A and B, and then plot the uncertainty of each. So delta A squared would look like this, and delta B squared would be this. Then what the Heisenberg-Robertson uncertainty principle tells us is that the area of this square has a lower bound. It cannot be any lower than the value on the right. So no matter how delta A squared changes or how delta B squared changes, the area must be greater than or equal to this value. And if A and B happen to be compatible observables, which means their commutator equals 0, then this area vanishes. But in the specific case, when the observables are position and momentum, no matter how small you might make one, the area of this rectangle can never be smaller than h bar squared over 4. Okay, so that's how the Heisenberg-Robertson principle is related to the original Heisenberg uncertainty principle. It's a generalization that can apply to any observable or self-adjoint linear operator. But where does Schrödinger fit into all of this? How could he have possibly improved this relation? Schrödinger's contribution came in two steps. Now remember, the right-hand side of this expression contains the commutator term AB minus BA. Schrödinger's first step was to consider what would happen if AB was written in another form. The second step was then to not just consider the operators A and B, but instead to replace them with new operators A minus alpha times the identity and B minus beta times the identity, where both alpha and beta are real numbers. By simply taking these two steps and carrying out some brief calculations, Schrödinger was able to show that an additional term can be added to the right-hand side of the inequality. Therefore, the inequality can actually be strengthened to look like this, where this term in the square is the covariance of A and B, which is just a quantitative measure of how correlated A and B are. So Schrödinger's insight was to see that the previous uncertainty principles only covered the cases where two operators happen to be not correlated at all. For any case where the two operators under consideration happen to have some correlation between them, then this more general equation would need to be applied. And the beauty of this expression is that it's the most general expression of the three uncertainty principles I've mentioned, and it indeed contains the other two. So all you need is the Schrödinger uncertainty principle. In the specific case when A and B are completely independent and have no correlation, then what results is the Heisenberg-Robertson principle. And in the case when A and B are the position and momentum operators, the Heisenberg uncertainty principle appears. So both the Heisenberg-Robertson version and the original Heisenberg version are just two specific cases of this more general uncertainty principle. Now, before ending this video, I'd like to make a brief note about terminology. Although it's by no means unanimous, there's a trend in some quantum mechanics papers and textbooks to make a clear distinction between uncertainty principles and uncertainty relations. And the distinction is the following. An uncertainty relation refers to how the manner of preparing a system can lead to a spread in measurement outcomes. A principle, on the other hand, refers to this as well as to how a particular measurement device can lead to a disturbance in measurement outcomes and to how incompatible observables cannot be measured simultaneously. So in the case of position and momentum, the original Heisenberg uncertainty principle says two things. One cannot prepare a system such that position and momentum are both precisely known, and one cannot accurately measure the position without disturbing the momentum and vice versa. However, in terms of this distinction, what I've been calling the Heisenberg-Robertson uncertainty principle and the Schrödinger uncertainty principle should technically be called relations. And the reason is that they are results that are derived based on the way physical systems are prepared. They do not say anything about how a measurement disturbs a system. If you want to check this out for yourself, I highly recommend taking a look at Schrödinger's paper where he derives his uncertainty relation. And I put a link for you to an English language translation of it in the description section below. Now, this terminology is by no means unanimous. In fact, you will see many authors using these terms interchangeably. But nevertheless, in certain circumstances, this distinction can be quite useful in clearing up confusion about exactly what type of uncertainty is being discussed.